Hello and welcome. Today we are diving into something that, I'll admit, sounds a little heavy, the harmonic oscillator. But I promise you, this one idea is actually the secret rhythm of the universe. It's beating at the heart of almost everything, from a simple toy to the deepest mysteries of quantum physics. So, to get us started, here's a little puzzle for you. What could a vibrating guitar string, a radio that's tuning into your favorite station, and a single tiny atom possibly have in common? I mean, they couldn't seem more different, right? One's about music, one's electronics, and the other is the fundamental stuff of matter.
Well, the answer is pretty mind-blowing. All of them, every single one, are governed by the exact same simple rule. They follow the same mathematical blueprint. And that's what we're going to unpack today.
Okay, so how do we get a handle on a rule that's so universal? Well, we're going to start where all good physics starts, with a perfect, idealized model. Think of it as the absolute blueprint for this rhythmic motion. And here it is. This is our hero for the day. A simple weight, a mass, hooked onto a spring. You pull it down, you let it go, and it just bobs up and down, up and down. That simple motion, that oscillation, that is the perfect picture of a harmonic oscillator. And this is its DNA. Now, I know an equation can look a little intimidating, but stick with me, because the idea here is incredibly simple. On the left, you've got mass times acceleration. You probably know that as force, right? F equals ma. And on the right, we have minus k times x. All that's saying is that the force the spring pulls back with is proportional to how far you've stretched it. And that little minus sign, that's the key to everything. It just means the spring always wants to pull the mass back to the middle. That's the whole rule. So when you solve that DNA equation, you get this beautiful, elegant answer. This is basically a roadmap. It tells you the exact position of that mass at any moment in time. And as you can see, it describes a perfect repeating wave. To really get it, we just need to know what those three letters, A, omega naught, and delta, are doing. First up is A for amplitude. This one's easy. It's just how big the swing is. If you pull the mass down a little, you get a small amplitude. If you pull it way down, you get a big amplitude. Simple as that. Next, and this is the really crucial part, is omega naught, the angular frequency. This is the system's natural rhythm. It's built-in wobble speed. It's determined only by how heavy the mass is and how stiff the spring is. You can't change it unless you physically change the parts. It's the oscillator's unique fingerprint. And finally, we've got delta, the phase. This just tells us where in the cycle the motion started. Did we let go from the very top, the very bottom, or somewhere in the middle? And that's it. Those three ingredients perfectly describe our ideal, perfect swing. So that's our oscillator in a perfect world, swinging back and forth forever. But, the real world is a lot messier. So let's see what happens when we start adding a couple of real-world forces into the mix. Right, so in the real world, two things get in the way. First, you've got friction. Physicists call this damping, and it's what makes the oscillation slowly fade away. Our spring isn't going to bob forever. Second, you can give it an external push to keep it going. This is called forcing. And this is where the magic happens. What happens when that external push, that forcing, is applied with just the right timing? Well, this leads to one of the most powerful and honestly coolest phenomena in all of physics. You already know exactly how this works. Think about pushing someone on a swing. You don't just shove them whenever, right? No, you instinctively time your pushes to match the rhythm of the swing. And with a bunch of little perfectly timed pushes, you can get them swinging incredibly high. That feeling, that perfect timing, that's resonance. And this graph shows it perfectly. The vertical axis is the amplitude, how high the swing goes. The horizontal axis is the frequency of your push. Now watch. As your pushing frequency gets closer and closer to the swing's own natural frequency, omega naught, the amplitude just skyrockets. The system basically soaks up the energy and goes wild. That dramatic peak is the telltale sign of resonance. So, a mass on a spring. Big deal, right? Well, here's the kicker. As the great physicist Richard Feynman loved to point out, the amazing part isn't the spring itself. It's the pattern, the equation that shows up over and over again in the most unexpected places. Feynman's whole point was that the universe seems to reuse its best ideas. The equations that describe one thing often describe something totally different, just with different labels. If you understand one system deeply, you've got a head start on understanding a whole bunch of others. And this right here is a perfect example. It's like a Rosetta Stone. On the left, our familiar mechanical system. Mass provides inertia. It resists being moved.
Look at the right. In an electrical circuit, an inductor provides electrical inertia. It resists changes in current. The friction that slows our spring down is just like electrical resistance in a wire. And the stiffness of the spring? It's the exact mathematical cousin to a property of a capacitor. The analogy is shockingly perfect. And this isn't just some cute comparison. This is literally how your radio works. When you turn that tuning knob, you're actually changing the properties of the circuit inside. You're changing its natural resonant frequency. You adjust it until it perfectly matches the frequency of the station you want to hear, and bam, resonance kicks in, the circuit massively amplifies that one signal, and all the thousands of other radio waves in the air are completely ignored. But the story doesn't stop with radios. Believe it or not, this same simple idea takes us all the way down to the building blocks of reality itself. We're going quantum. You know that old picture of an atom with electrons orbiting the nucleus like little planets? It's not really right. Feynman explained that a much better way to think about how electrons interact with light is to imagine them as tiny masses held in place by invisible springs. And that insight changes everything. The reason an atom can only absorb or emit very specific colors of light is because its electrons are behaving like tiny harmonic oscillators. They have their own natural resonant frequencies. An electron can't just have any old energy. It can only exist at these special resonant levels. And those allowed frequencies, that's what we call quantum energy levels.
So let's just pause for a second and appreciate this. The same simple math that describes a weight bobbing up and down also explains how a radio picks a station out of thin air. And it forms the very foundation for why atoms behave the way they do. It's truly one of the most powerful ideas in all of science.
And that leaves us with one final big question. We started with a simple mechanical toy, and we ended up at the heart of quantum mechanics. If this one simple pattern connects so many seemingly different parts of our universe, it just makes you wonder, what other secret rhythms are out there? What other universal music is playing, just waiting for us to learn how to listen?